Moisture capacity is a crucial concept in atmospheric science, building design, and engineering. It refers to the maximum amount of moisture that air can hold at a given temperature. Understanding this correlation is essential for architects and engineers as it affects indoor air quality, material durability, and climate control systems. The moisture holding capacity of air is directly proportional to its temperature. As temperature increases, air can accommodate an exponentially greater volume of moisture. Conversely, when the temperature decreases, the air's ability to hold moisture diminishes, leading to condensation if the air becomes saturated. To illustrate this, I've created this interactive graph which shows the amount of moisture that can be present in the air at given temperatures based on values from the engineering toolbox. If you'd like to take a look at this graph yourself, the link can be found in the description below. Relative humidity, or RH, is the ratio of the actual moisture content in the air to the maximum moisture the air can hold at a specific temperature, expressed as a percentage. When temperature rises while the absolute moisture content remains constant, relative humidity decreases. Conversely, if the temperature drops, RH increases, potentially leading to condensation. The saturation point is the threshold at which air contains the maximum possible moisture at a specific temperature. Beyond this point, if the air cools, condensation occurs, forming dew or fog. However, if the air warms beyond the saturation point, it can absorb additional moisture. A common example of this phenomenon is the way warm, moisture-rich breath becomes visible in cold winter air, or how moisture condenses on windows during chilly weather due to the temperature difference between indoor and outdoor air. The ability of water vapor to remain in the air is influenced by kinetic energy. At higher temperatures, air molecules possess greater kinetic energy, allowing more water molecules to stay in vapor form rather than condensing into liquid. This explains why warm air holds more moisture than cool air. The dew point is the temperature at which air reaches saturation and condensation begins. Unlike general condensation, which can occur on surfaces, the dew point specifically refers to the atmospheric condition where moisture starts to transition from gas to liquid. Maintaining low dew points in areas like crawl spaces and attics is critical to preventing moisture accumulation, which can lead to mold and structural damage. Proper ventilation, dehumidification, and insulation strategies can help in achieving lower dew points. Warm air is often used in drying processes because it can absorb more moisture. For example, in industrial drying of lumber, textiles, or food products, increasing air temperature from 20 degrees to 50 degrees can increase its moisture carrying capacity by 380%. This dramatic increase explains why heated air is much more effective in drying processes. Temperature and moisture capacity significantly impact indoor air quality, comfort, and the longevity of building materials. Poor moisture control can lead to mold, deterioration of wood, and compromised insulation effectiveness. Best practices for managing moisture in buildings include selecting materials that can resist moisture damage, designing building envelopes to manage moisture movement, for example with vapor barriers to control moisture infiltration, proper insulation to prevent condensation on cold surfaces, and installing proper ventilation systems to regulate humidity, for example by employing HVAC systems that maintain optimal indoor humidity levels. The correlation between air temperature and moisture capacity is fundamental to understanding moisture behavior in buildings. As temperature increases, air can hold more moisture, which affects relative humidity and condensation risks. This relationship is critical for designing effective ventilation systems, managing indoor air quality, and preventing moisture-related issues in buildings. Architects and engineers must consider these factors to create comfortable, durable, and energy-efficient structures. If you enjoyed this video, take a look at this video, which YouTube thinks you'll like. Stay informed, stay inspired. TimberTalk.